Hello, good morning. Today we're going to look at the chapter 2.2, the geometric design of rods, vertical alignment. Previously, I've talked about the horizontal alignment of rods. Okay, so these two, the horizontal and vertical alignments, they are both two parts of the geometric design of rods. Okay, so the horizontal alignment will look into the horizontal component, and the vertical alignment look into the vertical components of the rod. Okay, so they'll be look at the like grades going uphill and going downhill and so on. So the vertical alignment of the rod is known as a grade line. There's quite a few terms. Grade line, sometimes just called grade, in terms of percentage. The profile, the longitudinal section, or just simply the long section. So this is in a drawing. The bottom part of the drawing, usually for the, let's say, the detail of design, usually the top part is a profile or the plan. The bottom part is it's a long section. Okay, so this one is it shows the alignment of the rod vertically. So you have shown this one in terms of the percentage. This is vertical curve. I think there's a percentage here. Probably can't be seen from here, but this one on the left and on the you show the slope of this tangent and going up, and the tangent going down as well. All the okay. The profiles consist of straights or grades joined by curves. So these are the grades, or the grades. That means that it can be positive or it can be negative. So it going uphill is positive, going downhill is negative. These curves, known as the vertical curves, to distinguish them from the horizontal curves, are defined by two parameters. So we have horizontal curves, and then we have the vertical curves. So these two parameters are the comfort factor, which provides the smooth passage from one grade to another. So if you go uphill, you will have a positive grade, and then when you reach the top, and then you descend the hill, and then it'll be a negative grade. Secondly, a safety factor which ensures driver have a safe sight distance over the full length of the vertical curve. So this is the safety aspect. So this to ensure that the driver can have a safe sight distance. Essentially it's for stopping, so when they see there's any hazard in front, they can stop in time before the hazard. The profile is therefore the reference line by which the elevations of the pavement and other features of the rods are established. Okay, so this is a reference line. The factors to be considered in the development of the profile, factors to be considered. So there are quite a number of them. 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. So these are the things that we need to consider when we do the vertical alignment. The topography, the land, whether it's flat, whether it's rolling, whether it's mountainous. The rod types. So there are different type of rods. This one is a dual carriageway. This one is a mountainous rod. You're going up the hill. You have this one. It's a the rod type. This one probably just it could be just state highway, or it could be local roads near to the within the district. This one is just off-road, you know, it's accessible by the off-road vehicle, the four-wheel drive vehicles. So this one probably just it could be just this one. There's no need for any design, but the other three that we need design for them. Horizontal alignment, which we have covered previously. So we need to take into account the horizontal alignment, and later on in this chapter we'll look at the coordination between the horizontal and vertical alignment in terms of the safety, in terms of the aesthetic point of view, and also in terms of the drainage. Okay, side distance, we need to consider the side distance. Okay, so side distance is essentially to stop before any hazards, okay, any things on the road, or also for overtaking as well. So there's you want to overtake, you make sure if you go you're able to see any hazard in front, because if it's straight line, it's essentially on the straight line you can see quite far ahead, but on the vertical curve probably you need to have if it's straight line, if it's there's chance of overtaking, you know, they need to provide this safe overtaking distance as well. Drainage, so we have to consider drainage as well. Okay, so make sure that it's not the road is not at the sack here, it's not too low, it must be above the flooding, above the highest flood. Okay, whether depends whether it's designed for 20 years, once in 20 years, 1 in 50 years. The heavy vehicle operational characteristic. So if your road you have heavy vehicle, you have to consider, you know, whether the truck, whether it can go up the hill. Like this one is probably an off-road vehicle, it has no problem to go up the hill, but a lot of the other trucks, you know, if it's too steep they cannot go up, so you might have to limit the grade. You know, if there's a lot of heavy vehicles, these trucks or buses or other commercial vehicles, the trailer, the semi-trailer, you know, they use the road. If there is not many, if it's the road there's not many heavy vehicles, probably you can you have more freedom to use the steeper grade. Appearance, okay, we need to design the road. Actually, for both the horizontal and vertical alignment, we need to have present a very nice appearance and good aesthetic. You know, we look at that. It's not when you look at the road, it's not an eyesore. Rather, you know, it's quite pleasing. You know, it's blended into the landscape. Land purchase and construction costs. So this one is about the budget. We preferably we don't want to have too steep for vertical alignment, the slope too steep, or and then, but it's sort of is limited by the construction cost. You know, if you have too much cut, probably it's going to cost a lot for the earthwork, and yeah, so the grade of the road, how the grade, especially to the cut area, is governed by the construction cost, and also for the embankment area. We are quite conscious about we have tight budget, probably you cannot have too much embankment, or we cannot feel too much because it's going to burst the budget. Cultural development, so the vertical alignment, the horizontal alignment, it may have some cultural development as well. In New Zealand, if there's anything beside the road, beside any of the Maori heritage or site, you cannot have a very the road, the driveway, the access road to this cultural sites or the archaeological sites is too steep going down the slope. It must be we need to consider this aspect. This accessible. They can go down, or even like, for example, even the cemetery. You need to provide easy access to those sacred sites. The profile must ensure that all relevant design speed, site distance requirements are met at every point of the rod alignment. So the rod, whether it's designed for 80k or 100k or now even 110 km/h, both the horizontal alignment and vertical alignment, they need to meet the site. This one the site distance requirement. That means that you travel faster, you need to have a longer stopping site distance. Okay. So we have the site distance have to be designed accordingly. If it's 55, this if the rod is so both horizontally and vertically, if it's 55, because the site doesn't allow to have a higher design speed. So you have to if the site, generally it may be 80k, but in certain places you cannot achieve that. You probably have to put a sign saying that this part of the curve you need to slow down to 50k, 55k. It's good design practice to make the vertical alignment design speed 10 to 15 km/h greater than the horizontal alignment design speed to provide additional safety margin. Okay, so this one, according to the literature, it's good to to have a higher speed limit for the vertical alignment. In flat terrains, the profile is often determined by drainage considerations. Example, if the rod side drain is at a gradient of 0.3%, then let the rod be at that gradient as well. So that means that the drain, roadside drain, whether it's urban road or rural roads, they have they need to flow at a gradient like 0.3% is 1 in about 1 in 3 1 in 300. 1 in 33. Okay, 0.3 30 1 in 33. Sorry, 1 in 300. Okay, so 1 in 300. That will give us 0.33%. 1 in 300. So it means 1 vertical, 300 horizontal. So actually to get the 0.3%, actually need to be 1 vertical and 333 horizontal. Okay, so that gives us 0.3%. So if the thing is that some place is very flat, but if you sort of if you don't have a flat 0% the gradient of the rod, but the drain will be going deeper and deeper. So that's the thing, it's getting deeper and deeper, and then you probably have to provide some, if it's too deep, the drain is too deep, it can you have to maintain, there might be erosions aspect. But if you follow the gradient of the rod and the drain, the gradient of the rod, you follow the gradient of the rod 0.3%, then you can maintain a constant depth of the drains. So that's that's a good thing. So you don't need to worry about the drain being too deep on the side of the rods. In rolling terrains, some undulations in the profile can allow a more economic construction. So if the terrain is up and down, it's rolling, so it means that it's not too steep yet, but so it's up and down, so it can be, if you, that means that you follow the terrains, you just probably it's cheaper, there'll be less earthwork for the construction, so this is a cheaper package. The appearance of the rod must, however, be carefully considered in these cases. Example, a straight horizontal alignment which has a series of humps which are visible for some distance ahead should be avoided whenever possible. That means that, even though the terrain is up and down, if the road is straight, if you follow the terrains too closely, it is not, is probably appearance wise it's not nice. This one is a straight road, but if you sort of it's up and down, it's not so pleasing compared to straight line. It's a straight, so there's no vertical curve, so everything is straight. You can see further straight ahead, because this one, some of the vehicle may be hidden at the valley here. Okay, but sort of we do have to follow, the cost wise, if you have to fill up every valley, it's going to cost quite a lot of money. So actually, I think the guide, for the curve, you can have some curvature, but you need to have, it's desirable to have a big radius. Okay, your curvature, you have a big radius. So that means that if you have a short, we don't want to have a short vertical curve length. Okay, we want to have a longer vertical curve length for safety reason and for aesthetic aspect. The vertical alignment of a rod affects travel speed, safety, and its appearance. Okay, so this quite self-explanatory. The effects of grades can usually be ignored, however, when assessing the likely travel speed of light vehicle, because these are governed by more by the aspect of effects of the horizontal alignment than by vertical alignment. However, the heavy vehicles are very much affected by the steep grade. So the light vehicles, the small car, the motorcycles, all these light vehicles, they can even accelerate up the hill. But for the heavy vehicle, it's a semi-trailer, they're affected. The truck, the logging truck, they take a long time to, it's affected a lot. This heavy vehicle, they will slow down at the when it's going uphill. So probably like a lot of the roads, if it's a two-way road, at the hillside, when there's a steep ascent, or if you're going up the hill, usually they have this overtaking lanes at this part of the place, where the heavy vehicle you tend to slow down. So vertical curves are described as crest or set curve depending on the orientation. So the vertical curves are two types. One is a crest or set curves. Crest, that means they're going up and going down. Set is going down and going up. We'll look at it later on. So this one, I'm not going to open up the YouTube. You can look at it at your own time. So there are 6 possible variations of vertical curves, illustrated in the next 2 trigger. So this one is the crest vertical curves. So as long as you satisfy this aspect, you have a positive, this one, the not really positive, you have what is it called, a concave. The curve is this way, it's called concave, isn't it? Convex, I think it's convex, isn't it? The other one is concave. So if it's your curve is going up, where you curve upwards and going down the radius, then these are the crest vertical curves. So Usually it can be go uphill, go downhill. It can be this one. The first case is you have uphill and downhill, but the second one, both of them is going uphills. Just that the G1 is steeper. This part is steeper than the G2, and for the other one, the third one, both of the this one is also crest curve, but just that the first part is the slope is milder than G1 is milder, smaller compared to G2. G2 is steeper slope going downwards. The concave, this one is a sec vertical curve. Okay, so the yes, it could be so it's going down the valley, and this one the first case going down and then going up. So minus G1 plus G2. Or it could be going upwards, but just such the curve is like that, concave. So that means that both are positive. Just that the first part G1 is the slope is milder compared to the next one G2. G2 is steeper, and then can going downhill as well. The first part is steeper. Minus G1 is steeper, and then minus G2. This one G2 is the slope is flat, is milder. Okay, so usually the A is the algebraic difference in grade. So the G1, G2, whether it's the sec curve or the crest curve in the previous page, when you see the differences, you just add up. Then we have to take account the negative and positive signs. Visibility and comfort are the most important factors in vertical curve design. So the visibility. So when you design a curve, you need to look the visibility. Visibility in terms leads to adequate side stopping distance. So that is also safety. If you can see the hazard sufficiently in sufficient time, then you are able to stop in time before hitting stop in time without hitting the hazard. So the comfort as well. Especially if you have very short curves, going uphill, short curve length. And then the change of direction is so fast, it's not gradual. It's very rapid change up, and you go up and go down, or you go down the valley, going down and going up. So it's probably if it's the vertical curve length is too short, the change is too abrupt. So that could be very uncomfortable, and then people may experience motion sickness and throwing out. Crest vertical curve must provide stopping side distance for the design speed of the horizontal alignment. Where possible, side distance should be increased to provide passing opportunities. So the side distance is to provide the adequate distance for stopping and also for overtaking. So this is a curve, crest curve. Okay, vertical curve must ensure vehicle occupants' comfort, i.e. the rate of vertical acceleration, the headlight performance criteria must be met. So the sec curve, which is like this, you have no problem to look at what is coming from in front from the opposite direction. So comfort, sometimes it's like the curve is the changes is too fast, so if it's go up, go down and go up, then it could be very uncomfortable. So that it could make the the occupants feel uncomfortable and experience motion sickness. And also the night travel, the headlight beam, they have some sort of the distance. There are some limiting distance, so you need to be the headlight distance. You may need to be able to see how far in front, so that you can spot any hazard in front. Otherwise, so we need to consider the headlight beam distance as well. Yeah. So is that you must consider comfort, and then the headlight distance. So this one, so this curve is quite it's quite good, because it is the vertical curve is the radius probably is not too big, so it's not too small, and then it's quite a long vertical curve length. So you can see quite clear in front, quite clear in front as well. Any vehicle coming, any hazard in front, and this one, if you go up the hill or go down the hill, the side curve, be able to see the any things in front, any hazard, any animals crossing the road, yeah. So, but for the the vertical, the crest curve is probably not so much, because crest curve, the headlight you can't see too far ahead as well, because the headlight probably is not the one that is important, because if you shine, the beam will go directly above. You cannot see through the hill also, so the headlight is not the critical here. But for this one, yes, your beam probably is certain distance only, like 150 meter, so you must design for that. Other factors for the set curve need to be considered are the drainage requirement. Okay, so set curve, so if it's too radius is too small, you probably you're going to experience some sort of this one, the going to be going down too low, so below the flood level, which is not desirable. Other thing is that the set the set curve, the radius is the obstruction. There's a bridge. You make sure that you need to provide the clearance to enable the design vehicles to pass through. Certain, I think there's a certain height for the make sure that the trailer, carrying some container can go past. Otherwise, I think as we have heard before, that the goods at the back of the truck being hit the bridge, and then the whole thing fell over. We don't want this type of disruption. So there must be enough clearance for the vehicles. Especially they carry some equipment, some trailers pull sort of have some, this one digger at the back, where the arm is too long, you might hit this one bridge. So we need to provide sufficient the clearance, the height from the rods. Grades. Rod grades are normally expressed as percentage. Okay. A rising grade is a positive grade, and the negative grade is a falling grade. Okay. We don't say how many degree the uphill or downhill. We do the certain calculations. If you do the other things, if you do a mathematical problem, the application probably say 20 degrees up, 30 degrees up, and 20 degrees down, or something like that. But for rods, we usually talk about the grades in terms of fraction or percentage. We sometimes say 1 in 30, 1 in 20, 1 in 50, 1 in 100. So so for example, this one, the grade is 8.02%. This is going uphill, and this 8.02% actually is 1 in 12.47. 1 in 12.47. So this is how we measure the grade of the rods in terms of percentage or in terms of the ratio 1. Okay. Minimum grades. Okay, so certain minimum state highway grades are set by the need to provide adequate drainage along the rods of water from the road surface and are shown in the table. So for this one, the long section, the minimum grades is the rod with curb and channel is 0.3%. The uncurbed rod in cuttings. Okay, there's a rod in cuttings. You cut through hill. It need to be 0.5%. Okay, if uncurbed rod in all other situations. Okay, in all other uncurbed rods. So this one, the cutting, you will need to have uncurbed rod in cuttings. You need to provide the roadside drain. So the roadside drain, you need to provide some gradient for the roadside drain. But uncurbed rods in all other situations, because like this one, the curb and channel, that means that there will be this one is the urban rod. You need to provide the stormwater pipes. So that one, the 0.3% is 1 in 333. So that provide the gradients for the water to flow in the stormwater pipes. But for the uncurbed rods, sometimes there's no uncurbed rods. If it's not in the cutting, if it's embankment, sometimes they just they don't have roadside drain. They just water just fall freely down the slope, the embankment slope. Okay. So this one, the minimum grade is 0%. A level grade can provide adequate. A level grade can provide acceptable drainage condition on uncurbed rod in flat terrains, provided the roadway is adequately crowned and there are no problems in removing the pavement surface water runoff by table drains or ditches. Yeah. So okay, just now I said that the water, you still have normally even though it's an embankment, you still have this table drain. We should not. Sometimes I have seen some road, they don't have table drain beside the embankment. Beside the road in the embankment. So but they need to have protection for the embankment. They have sort of your slope, the water can flow down the slope, but not for the whole slope. They usually have a steps. The slope they can only fall by let's say 5 meter. You cannot like fall if the slope is about 20 meter. You cannot just the whole water just run down. It will create a lot of erosion. So usually is they have step. They got the one stage of the slope, and then they have a berm, and along the berm they have some drains to collect the water, and then you have another slope. So you have different slope. So they break into different slopes, not just single slope down to the high embankment, high cuts area. Same thing for the embankment as well. If you have a tall embankment, they break into different slope with berm in between. So usually the this one, if the rod is uncurbed rod is adequately crowned, the water can be removed as well. You see, usually the rod is for the two-way two lengths two-way rod. Usually the rod will fall from the lens. It will it will have a slope from the center to the side. This is a curve with the curve and channel. So this one is for at 2.5%, which is a ratio of 1:40, 1 vertical, 40 horizontal. So same thing for the other side, the right hand side as well. So usually for two-way two-length rod, usually they fall from the slope from the middle to the edge. But sometimes certain place they might slope just across, especially for the this one the multi-lens rod, they just fall like 3 lengths, just same slope across. Okay. On curved rods in flat terrains, drainage problem can arise on the inside of the curves and also in the vicinity of zero pavement crossfall, which occurs within super elevation development lands. So this one, if it's a curved rods and it's flat terrains, it could be a problem in the inside of the curves, as well as a place there is a zero pavement crossfall. So this one is the rod, you have to ride the crown have to rest up to the level and then up to the super elevation, and then return back to the level and then to the crown again. So this part and show this part, it could be, if it's a certain the length could be quite long, if it's a big curve, if it's a for flat rod, it could be some problem. This part is the rod is no, there's no longitudinal grades, and then no grade on the transverse grade as well. And especially so, if it's a multi-lane two dual carriageway, one side is 3 lanes, it could be a drainage problem. And also the inside here as well is flat rod, so this one could be the water may accumulate at the inside of the curve here. In these areas of curved rod, some longitudinal grade must be provided to maintain the water depth within acceptable limits, and long plane transition spiral curve should be avoided to reduce the extent of flat crossfall. So for the curved rod, it's good to provide some sort of grades. Okay, the longitudinal grade, you like minimum, we say that it's like 0.3%, 0.5%. Because if it's flat zero, the water is not moving, then there might be some this one, the water problem, or drainage problem on the surface of the rod. It could be ponding, or even a film of layer water on the surface of the rod. It could be hazardous as well, because I think it could create some sort of aquaplaning, the water, because there will lost the vehicle will lose contact with the ground, and so it will sort of cause the vehicle to slide along. At the large intersections, it's important to avoid operational problems related to surface water ponding by ensuring the combination of crossfall and longitudinal gradients at least 2.5% for chip seal surface and at least 2% for smooth asphalt surface. So you must be able to provide, if the intersection, you must the resultant crossfall, they have a long section, long longitudinal gradient and crossfall. The resultant need to be like 2%, 2.5 or 2%, so that the water will able to slop. If it's too flat, it could be a lot of problems. in a very flat urban areas, it's preferably to use near level grades. Okay, having mentioned so many things, we need to provide grades, but in urban area, this one we probably we rather have flat rods, whereas level rod, because this one it is probably is no good for the appearance. Okay, so you can provide level grades by providing additional sums. So to get rid of the water, we need to provide more sum. This one the catch pit, so that the water can be drained off from the side of the rod, and because this thing, the water go into the catch pit, you go into the stormwater pipes. So instead of providing the grades, in a very flat urban areas, in the urban area, probably the solution will be not the increase the grade of the rod, but rather to provide more sum, okay, the catch pit to drain away the water. Artificial undulations can result in an unsightly appearance, which suggests faulty construction, particularly where the horizontal alignment is straight and nearly straight. So that's one is, if it's very straight and very flat ground, and then you got the undulations, then it's probably doesn't look nice. So this one, this one probably is not a level rod, but sort of you look at it, it's a straight rod, and then there's got so much undulation. It sort of give people the impression that there might be some structural problem of the rod. Maybe the rod is certain part is excessive consolidation. The rod is sinking or certain part. So the appearance wise is not nice as well. Maximum grades. Maximum rod grades are determined by vehicle performance, particularly heavy vehicles, and level of service criteria. Okay, so this is a very steep rod. I think this one is I think it's in Dunedin, Baldwin, is it BALDWIN? I think Baldwin Street. Okay, I think it's supposed to be the steepest street in the world. I think it's fighting with one in Wales, isn't it? I don't know what's the development. Is it this one is second or the steepest? Okay, so this one this depend on the vehicle characteristic. If you got like 4-wheel drives, Land Rover, they can go up very steep grade, no problem, 30%, 40%. I think this Baldwin Street is about 38% as well. It's very steep. Okay, so for truck probably have difficulty going up the road as well. So for the light vehicle probably it's no problem. But the thing is that for steep road in winter there'll be a problem because the place can be very slippery, and then I think we have another guideline of this place that you have snow or maybe black ice. I think they limit to 6%. But having said that, certain roads, we cannot, because of the development on both sides, you cannot cut down the slope. Certain places there'll be some exception. Okay, if you are going to do a new roads, in some case approval may be given to increase the maximum grade permitted on the section of state highway after due consideration of the types of terrains, adjacent land use, financial condition, relative importance of the roads. If you design a new roads, whether it's urban road or rural roads, then if your road is too steep, like the one we saw just now is 38%, that one's really exceptional. even like if it's steeper than 10%, you have to get approval from the authority, the routing authority, whether it's like in New Zealand is whether it's the NZTA or the district council or city council. On high-speed roads, grade up to 3% provide road user with a good level of service and minimize the adverse effect of speed variance, different speed between different types of vehicle. So for high-speed road, usually we don't have a very steep grade. So usually, you know the 3%. Yeah, 3%. We don't want to provide so many because they cater for different type of vehicles. 3%, but I can't really gauge what is the slope of this one. Okay, as a guide, as a rule, normally it's 3%. Okay. On roads with more modest operating speed, grades up to about 6% do not usually cause noticeable problem with speed variance. Okay, if it's lower speed, I mean less sort of less vehicle, you know. Just now the one probably, you know, we look at this one probably 100k. So this one certain road, this could be 100k as well, but certain road you maybe it's 80k. So this one it could be, you know, is maybe there's less traffic on this road as well compared to the previous one. This one, so it could be up to like 6%. Grades steeper than 10% often cause speed variance problems. That means that you got the vehicles, if let's say it's open speed limit of 100k, some vehicles can still maintain 100k, but other vehicle, the truck may become crawling out down to like 20k, 30k. So up the hill, so there's so much variation. So it could be sort of a risk, you know, if the slow vehicle is not moving to the side, to the slow lanes, it could, you know, the fast vehicle might hit the slow vehicle in front. Okay. So steep hill also, it means that high speed down the slope as well. Okay, some vehicle, you know, this going up the hill maybe a bit front front light, isn't it? This one a bit of stunt here. The wheel of the truck is sort of been lifted up, the front wheel. Table 5.2 indicates the general maximum grades that should be used on seal-stacked highways in relation to terrain type and design speed. So the different design speed, let's say 60, 80, 100, 120, and a different type of terrains, flat, rolling or mountainous. So the flat one will be the gradient will be lowest. The rolling one is intermediate, and the mountainous is higher. But in this case, we still limit the maximum grade to 10%. Okay, 10%. So the flat one we go up to 8%. The rolling one up to 9%, and the mountainous go to up to 10%. Okay. So the grade less than lower limits shown in table 5.2 would normally be used on state highways, and grades steeper than 10% should be avoided. So the as a rule of thumb, the grade should be less than 10%. Long lengths of grade steeper than 3% will cause heavy vehicles to slow down as well. If you have like the slope, which is maybe not very steep but it's very long, it could slow down the vehicle as well. Like this one maybe, I don't know, maybe 6%. So the heavy vehicles, if it's a short if it's short slope, it probably can, the momentum can carry over to the top, quite sure. But if the lane is too long, it will slow down. You go up the hill, it might be crawling up the hill, and then if snow, all the vehicle will stuck behind, you cannot overtake on the up the hill, it will sort of, it cause traffic jam. In areas subject to frost or snow, grades should be kept as low as possible. Desirable maximum grade in this condition is 3% and absolute maximum is 6%. Just now we talked about the Bowen Street in Dunedin. That one is 38%. So there will be a lot of problem during the winter. The vehicle may not be able to stop downhill or even up. So yeah, that one is an exception. But as a general guide, if there's some place is susceptible to snow, or actually they need to be like 3% and most absolute maximum of 6%. But you look at that, some of the paths, it could be some of the paths could be quite steep as well. Even some of them is as steep as 10%. But sort of, it's a rule of thumb. Those places, they highly hazardous. They will have a lot of signage, to warn the vehicles, about the slippery condition during the winter. In areas of zero cost fall and within super elevation development area, surface water flowing longitudinally along the road can increase the depth to the point where aquaplaning occurs. Surface water flow depths should therefore always be checked on grades deeper than 6%. So sometimes the area there's a zero cost fall, the water will so the water cannot zero cost fall. That means that water, it cannot flow to the side. It can only go flowing down the slope. So it could be such if the road become a drain. So all the water is flowing downhill. It's very steep. The water can be quite fast as well. So it could be certain part of the road could be the water film could be quite deep. So it will the going flowing down. So we need to check for the aquaplaning as well. So much water going downhill. So we need to make sure that we need to check for drainage. Steep grades. Although the general maximum grade for all step highway is 10%, there may be circumstances where steeper grades are unavoidable. In mountainous, example in mountainous terrains, the use of grade steeper than 10% require approval of state highways, approval of highways strategies and standard managers. So the road is very steep road, the 10%. Later we see that's 30%, 15%. So how is it translated into? 10% is 1 in 10, 15% is 1 in 6.67, 30% is 1 in 3.33. So these are the percentage in relationship with the fraction. So the rule, some of the rule of thumbs is that the cars can go up 30% slope, and the truck generally limited to 15%. So this in Bowen Street in Dunedin, the grade has 38%. You see how the road, how is it compared to the building? It just it's so steep. Even access to the driveway could be a problem. This one is exceptional cases. The following situations are example where the use of grades steeper than the general maximum may be warranted. So sometimes we uh, the the grade steeper than 10% can be approved. Firstly, comparatively short section of steeper grade which will allow significant construction cost saving. So if your stop is the steep grade is quite short, let's say it's quite short, so usually this one is it can save maybe in some cases it could save some construction costs, because this one is short. That means that the vehicle going down, they can carry some speed momentum, and then they can go up the hill, without being excessively being slowed down. Second, difficult terrains where achieving the general maximum grade is not practical. Difficult terrains. So like this one, quite considered as quite difficult terrains, going up the hill, straight up. This one is normally, we don't usually go up a hill with zigzag, going left, going right, so that cover more distance, so that the stop is gentle. But if you have a direct straight line up, the stop is going to be steeper. So but this one maybe but because this one you go straight up, it's cheaper. If you go zigzag, the line is longer, then it will cost more. So that's difficult terrains where very few heavy vehicles use the road. Okay, if certain road, maybe, for example, the one we saw just now, this one, no heavy vehicle can climb this hill, so probably 0% heavy vehicles, except for those military trucks. Otherwise, so if there are not many heavy vehicles using the road, probably you could use certain part of the road section to be like more than 10%. Okay. Lastly, local roads where the cost of achieving high standards are less able to be justified. Local roads, for example, this one just country roads, this one's unsealed road. The state authorities not going to spend heaps of money to build expensive road to do a lot of heavy cutting. So this one probably is justifiable. Okay, so these are the situations where sometimes the maximum grade can be permissible. Vertical curves. So we're going to look at the vertical curve for a while. The various curve forms are suitable for use as vertical curves, but the parabola has been traditionally used because it gives a constant rate of change of grade, which maintain a constant driver's side distance. So we normally use a parabola as the for the vertical curve. We not for the horizontal curve we use a circle or the spiral. Okay, but for the vertical, in this case we use a parabola. So this one is a parabola curve. So we look at that. So there are certain things that we need to see. This is the horizontal length. The curve, this is a curve length, but we measure the horizontal length. Okay, so the all the distance actually in the vertical alignment, they are all measured in horizontally. We not measure the curve distance, the curve length, because the changes of the rod is only based on the horizontal curvature. Okay, the horizontal curvature, not based on the vertical curvature. Okay, so otherwise, the rod, for the changes we need to take account the turn left, turn right, the horizontal curvature. But the vertical, we're not going to measure the rod how long is it up the hill, down the hill, because this the curve line will be longer than the straight line. So but we just the mileage, the change will based on the horizontal line of the rod. Okay, so for this vertical curve, so do you have the horizontal line, and then you have the radius. We have the here we call the VPC, and then VP vertical, I'm not sure what is it called. Sometimes we just call it the start of the vertical curve, end of the vertical curve, and then they have a intersection point. It's a V. Here they call VPI, but in the project we're going to call the VIP, vertical intersection point, as to be sort of differentiate from the horizontal curve. Horizontal curve for the intersection point is just called IP, intersection point. So we have this G1 percentage, G2, okay. So the L is the length of the vertical curve, A is the algebraic difference of grades, algebraic. So the grades will be just plus G1 plus G2, but this one will be the slope, the down slope will be negative, uphill slope will be positive. Q is the rate of change of grade per unit length. Okay, so where's the Q? Yeah, here Q. So the change of grade per unit length. So you just for 1 meter, how much is it change? So for a simple parabola, the rate of change of grade per unit length is constant Q. So the how many percent? This one is the algebraic difference. You know, the going up maybe 10%, going down 5%, minus 5%. So you add up is the A is 5%, but length of that it could be 100 meter long. You know, so that's that give you the Q. And now this one is more. The K is being used more, I think, frequently. Is I think we most of the time, you know, we define the slope, we use a K instead. So K, the reciprocal K is defined as horizontal distance in meter, which results in a 1% change of grade. So your grade maybe from you know, it is either is a convex or concave. So there's a change of grade. So for 1% change, what's the length being traveled? You know, it could be like 10 meter for 1% change. So that means that, you know, 10 divided by 1, so your K become 10. For A is a 1% change. Okay. So the same thing, L is the length of vertical curve, A algebraic difference of grades, K length of vertical curves for 1% change, Q the rate of change of grades per length. The K values concept is simple and convenient methods for designating the size of vertical curve. For each design speed and side distance configuration, a different value of K defines the length of the curves for all value of A. Okay. Later on we'll see more on this the K value. Okay, we have a K value for the vertical, for the crest curve, and we have the K value for the set curve as well. Also the designing for designing purpose, a vertical curve can be plotted using a circular curve of radius r, which approximate very closely a parabolic curve. So when you draw the vertical curve, we still can use the approximate it by the circle. Okay, and then in this case r is equal to 100k. If you know the k, then you just multiply by 100. That give you the radius of that vertical curve. So this one you still use the circular curve to approximate the parabolic curve. So this is just an example. You know, the this one, the uphill is 2.5 plus 2.5%, going downhill is minus 1.5%. So the algebraic sum is plus 2.5 plus 2.5. Let me see. Sorry, the algebraic difference, G1 minus G2. So plus 2.5% minus 1.5, that gives us 4%. And then the K is equal to what's that? K is equal to L divided by A, isn't it? L divided by A. K is equal to L is 250 divided by 4. 250 divided by 4, that will give us K equal to 62.5. R is equal to 100K, so it's 100 times 62.5. So that's radius. The length is given. Okay, so this one, 100 multiplied by 62.5, which give us what's that? 6,250. Okay, for the radius. Yeah, the radius is 6,250 meters. The radius. So this one, I think we have mentioned it earlier. K values for vertical, for the crest curve. So like they got so many K here, K value. One is a stopping requirement, one is for overtaking requirement, so you probably cannot see properly. There are some K values for different, based on the height of the hazard, you know. The hazard one is very low, one is 0, okay, and then one is higher, almost as high as the driver's eyes. So this one, yeah, so you look at the hazard here, this is the object height, and then this one you look at the car on the other side of the road. Okay, so like this one is mostly for the overtaking side distance. Okay, the set curve is the K value, one for the headlight side distance control, the other one for vehicle occupants, right? Right. So normally we look at this one, the headlight side distance. This one is the controlling. Okay, the one. Okay, the form of vertical curve. So the vertical curves, the usual form of vertical curves used is parabola. Okay, this parabola. Normally this is symmetrical. So you have so this one, the whole length is L. So from this one intersection point, so this one you'll be from here from the tangent point. So this one will be L divided by 2, both sides, from the tangent point of tangent to the intersection point is L divided by 2. L divided by 2. For this is symmetrical vertical curve. We measure the distance from the first the point of tangent. We start from here 0, and then we measure the horizontal distance is x. Okay, and then the vertical distance, how much is it going up from the parabola to the tangent is y. Okay, so and then at the apex, at the highest point, is e. Okay, the e. So these two distances are the same. Okay, okay, so I think these are the things that we have mentioned. The G1, G2 are the grads. L, E is the vertical distance from the IP to the curves. Okay, horizontal, X is the horizontal distance. Okay, Y is the vertical distance. S is slope to the tangent to the curve. Basic property of the parabolic curve. So I think I just briefly, I don't want to go too much detail here. So just that the parabola, if you study the mathematics, you know, is usually 2 power x squared. Y equal to proportion to x squared. It could be something else, you know, like for y is equal to 4ex squared divided by L squared. So these two, y and x, are unknown, but y is a vertical component, x is a horizontal component, but the relationship is y is proportionate to the x square, x to square of this. Okay, so this one, the relationship of the parabola is this relationship. Okay, and then we can find at the point when there is you know, when at this point when the slope is 0. Slope is 0 here. This part is 0 here, up here. But sometimes, you know, when the slope is this one, the slope is 0, then the x can be sort of become like this, simplify into this one. Okay. Okay, so I think I will stop here for time being. I will continue in part 2 later on. Okay, thank you.